Secure systems are rarely the result of a single brilliant control, and they are almost never rescued by a last-minute patchwork of fixes after the architecture is already set. What reliably produces safer outcomes is a set of design principles that shape decisions from the beginning, long before you choose specific products or write a line of code. These principles act like guardrails because they help you reason about risk in a structured way and keep you from relying on luck or on one fragile assumption. They also help teams communicate, since a principle gives you a shared vocabulary for why a decision is safer, not merely that it feels safer. When you apply principles consistently, you get architectures that are easier to operate, easier to monitor, and easier to recover when things fail, which is ultimately what security is trying to enable. Before we continue, a quick note. This audio course is a companion to the CISSP books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Defense in depth is the practice of using layered controls across components so that failure of one control does not immediately become failure of the system. The idea is straightforward. Assume that any single safeguard can be bypassed, misconfigured, or disabled, and design so that an attacker must cross multiple independent barriers to achieve the goal. Layers can exist at many points, including network boundaries, authentication, authorization, application logic, data protection, endpoint hardening, and monitoring. The value of layering is not redundancy for its own sake, but the ability to slow down attacks, limit blast radius, and provide more opportunities for detection. When you design layers well, you avoid the brittle situation where a single mistake, such as an overly permissive policy, becomes a catastrophic exposure. Least privilege is the principle that access should be limited to the minimum needed for a task, role, or process, and it applies to people and to machines. In practice, least privilege means permissions are narrow in scope, time, and capability, so identities can do what they need to do, but cannot easily wander into unrelated systems or sensitive data. Least privilege is not a slogan, it is a continuous design choice about how you create roles, how you delegate authority, and how you keep permissions from accumulating indefinitely. It also requires clarity about what the task truly needs, because teams often grant broad access simply to avoid the effort of defining precise rights. The payoff is significant because compromised credentials are one of the most common attack paths, and least privilege turns a credential compromise from an enterprise-wide crisis into a more containable incident. Separation of duties is closely related, but it focuses on dividing power so that no single individual or process can complete a sensitive action end-to-end without oversight or cooperation. The purpose is to reduce misuse, whether intentional or accidental, by ensuring that critical changes require multiple independent approvals or multiple distinct roles. Examples include separating those who request access from those who approve access, separating those who develop changes from those who deploy changes, and separating those who administer systems from those who administer keys or logging. This division also reduces the chance that a single compromised account can both make a change and conceal the change, because oversight is embedded in the workflow. When separation of duties is applied thoughtfully, it supports governance without paralyzing operations, and it creates natural checkpoints where anomalies can be caught early. Fail-safe defaults is the principle that access decisions should default to denial, and that explicit permission is required to enable access. In a well-designed system, the absence of a rule should not grant access, and the failure of a component should not silently open doors. This matters because failures happen, and ambiguous defaults are a common way those failures turn into exposures, especially when systems fall back to permissive modes under error conditions. Deny by default also encourages deliberate design, because teams must explicitly define what is allowed and justify it, rather than relying on implicit broad access that nobody can fully explain. In operational terms, fail-safe defaults reduce surprise because new assets or new users do not gain accidental privileges simply by existing. When you combine fail-safe defaults with good observability, you also get clearer signals because denied actions are more likely to represent misconfiguration or misuse worth investigating. Economy of mechanism is the principle that designs should be as simple as possible because complexity hides flaws and makes auditing harder. Simplicity does not mean lack of capability, but it does mean avoiding unnecessary moving parts, unnecessary layers of translation, and overly clever logic that only one engineer understands. The more complex the system, the more difficult it is to reason about edge cases, and attackers tend to live in edge cases where assumptions break. Simpler mechanisms are also easier to test, easier to patch, and easier to operate consistently, which reduces the operational drift that often creates vulnerabilities over time. When security relies on a complex chain of conditions, it becomes fragile because a small change in one place can have unexpected consequences elsewhere. Economy of mechanism therefore supports both security and reliability by making it feasible to validate how controls actually behave. Complete mediation is the principle that access checks should occur every time access is requested, rather than relying on a one-time decision that can be bypassed or become stale. In modern systems, this means authorization is not something you do at login and then forget, because privileges can change, sessions can be hijacked, and context can shift during an interaction. Complete mediation also implies that internal calls and service-to-service requests should be authenticated and authorized with the same seriousness as external requests. If you allow trusted internal pathways to skip checks, you create a soft interior where compromise spreads rapidly after a single entry point is breached. This principle becomes more important as architectures become distributed because there are more hops, more services, and more opportunities for an attacker to move laterally. When access is mediated consistently, you reduce the number of hidden backdoors created by assumptions about trust. Open design is the principle that security should not rely on secrecy of the design itself, but should remain strong even when the design is known. This does not mean you publish sensitive configurations or expose secrets, but it does mean your controls should not collapse if an adversary learns how the system works. Relying on secrecy tends to fail because designs leak through documentation, behavior, error messages, and reverse engineering, and because insiders may reveal details intentionally or accidentally. Open design pushes you toward using well-understood mechanisms, strong cryptography, and robust access control, rather than relying on obscurity as the primary barrier. It also encourages clearer internal documentation and peer review because you are not treating the design as something too secret to examine critically. When you adopt open design, you build systems that are defensible under realistic threat assumptions rather than under optimistic assumptions about secrecy. Least common mechanism is the principle of avoiding shared dependencies across users or components when that sharing creates unnecessary coupling or risk. Shared mechanisms can become bottlenecks, single points of failure, and single points of compromise, especially when many users rely on the same service, the same credentials, or the same control plane. Reducing shared mechanisms does not mean eliminating all shared infrastructure, which is rarely possible, But it does mean limiting the scope of shared privileges, shared storage, shared administrative channels, and shared runtime environments. In practice, this principle supports isolation between tenants, isolation between workloads, and separation between environments such as development and production. When you reduce unnecessary shared mechanisms, you reduce the chance that one compromised user or one misconfigured system can affect many others. It is a way of designing for containment and for predictable failure domains. Psychological acceptability is the principle that security controls must be usable enough that people will follow them rather than bypass them. If a control is so painful that it blocks normal work, teams will route around it, and the resulting shadow workflows are usually less secure and less observable. Usability includes clear error messages, sensible defaults, minimal repeated friction, and workflows that align with how people actually perform tasks. This principle is not about making things easy at the expense of security, but about making secure behavior the path of least resistance. When controls are acceptable, compliance becomes the natural outcome rather than a constant enforcement battle. In well-run environments, psychological acceptability is treated as part of security engineering because human behavior is a primary factor in whether controls deliver their intended risk reduction. Secure defaults are the practical application of several principles at once because they determine what happens before any customization occurs. Defaults should be conservative for configuration, ports, and service exposure, meaning that services are not publicly reachable unless explicitly required and explicitly enabled. Default accounts should not have broad privileges. Default credentials should never be acceptable, and default logging should be sufficient to support detection and accountability. Secure defaults also mean that new instances of a service start in a hardened posture, with minimal open ports, strong authentication expectations, and baseline monitoring enabled. When defaults are unsafe, security teams spend their time chasing down misconfigurations across rapidly changing environments, and exposures appear faster than they can be corrected. When defaults are secure, the system starts in a defensible state, and deviations become deliberate decisions rather than accidental drift. Layered controls connect directly to detection, prevention, and recovery, because layers are not only barriers, they are also sensors and recovery enablers. Preventive layers include authentication, authorization, segmentation, and hardening, which reduce the probability of successful compromise. Detective layers include logging, monitoring, alerting, and integrity checks, which reduce the time an adversary can operate unnoticed and improve response speed. Recovery layers include backups, immutability, redundancy, and restoration processes, which reduce business impact when prevention fails. When you design layers with these three outcomes in mind, you avoid building a stack that is heavy on prevention but blind to misuse, or heavy on detection but incapable of recovery. The strongest architectures accept that failures and compromises will occur, and therefore engineer the ability to contain, understand, and restore. This mindset is where design principles become operational resilience rather than theoretical guidance. Privilege management is where least privilege and separation of duties meet the messy reality of administrators, services, and automated processes. Administrators often need broad capabilities, but those capabilities should be scoped by role, time, and environment, with higher assurance authentication and controlled administrative pathways. Services and automated processes often require privileges to function, but those privileges should be narrowly defined, rotated, monitored, and isolated so that a compromise of one service does not provide universal access. Privileged access should also be auditable, with clear records of who elevated privileges, why, and what actions were taken, because investigation and accountability depend on that evidence. Privilege management is not a one-time setup, because permissions tend to accumulate and persist, and drift is a predictable failure mode. When privilege is managed intentionally, you reduce the likelihood that routine operations create a growing pool of latent power that attackers can exploit. Design principles guide consistent, safer architecture and operations because they provide a stable logic for making security decisions across changing technologies and changing threats. Defense in depth ensures that no single control becomes a fragile linchpin, while least privilege ensures that identities cannot roam freely when compromised. Separation of duties reduces the risk of misuse and concealment. Fail-safe defaults prevent accidental openness, and economy of mechanism keeps systems auditable rather than opaque. Complete mediation and open design push you toward consistent enforcement and robust mechanisms that do not depend on secrecy, while least common mechanism and psychological acceptability reduce systemic coupling and increase real-world compliance. Secure defaults and layered planning connect the principles to daily reality by shaping configuration, exposure, detection, and recovery choices. When these principles are applied together, they produce systems that are easier to defend, easier to understand, and more reliable under stress, which is the real objective of secure design. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.